So this is 1.2, part 2. We're going to talk about step and piecewise defined functions. So first thing we have here is a step function. A step function is also known as the greatest integer function, which is denoted by this symbol here. So it's a bracket, but with 2 bars. Now, step functions are the greatest integer less than or equal to x. Does anybody know what integer means? So integer means that it is a whole number. So whatever's in our bracket, we're looking for the nearest whole number that is less than that. So we can't go over it. So it gives us a few examples. So it could also be equal to, so if we had the greatest integer of -1, the nearest whole number to that would be -1. If we had 0.5, the nearest integer to that without going over, so that is less than 0.5, would be 0. So if I had the greatest integer of, let's say, 1.9, what would be closest to this without going over? Awesome, 1. Perfect. What if we had -0.4? What is the greatest integer that's less than or equal to -0.4? -1, perfect. So -1 is less than -0.4. So here we have the graph of a step function. So this is just our step function. We'll get to piecewise functions on the next example. But this is what a step function looks like. Step function is also sometimes called the floor function. It kind of looks like steps on the floor. One way that we can graph it or figure out our graph is you can make a table of x's. So let's say I had -0.75, -0.5. Let's do 0, 0.5, 0.75, 1, and 1.5. So just to give us a few examples. So these are x. So if I'm asking for the greatest integer of x, the y that we would get, so if we had the greatest integer of -0.75, what is the greatest integer that is less than or equal to -0.75? -1, awesome. What about for -0.5? Also -1. So if I were to graph that, if I go to the left to -0.75, I'd go down to -1, so our point would be here. If I go to the left to -0.5, I'd go down, so our graph would be here. For 0, what's our greatest integer? 0. For 0.5, what's our greatest integer that is less than or equal to 0.5? 0. What about for 0.75? 0. If we graphed those, we'd have a point at 0, 0, 0.50, 0.750. What about for 1? 1. And what about 1.5? 1 also. So 1 would have a point there, and 1.5 would have a point there. So our graph is just like steps of a floor. So you could find your graph by plotting points and figuring out where. You're just talking about integers. So your y values are just whole number integers. Sometimes we may have transformations happening to our step graph. So I think the one on WebAssign is something like the greatest integer plus 1 or minus 1. So you could either take your parent function that we have here and shift it up 1, or you could just plug in numbers for x and plot your points. Now this is still a function because we it passes the vertical line test. We don't have 2 points that we would draw a vertical line on. That's because we have an open circle and a closed circle. So if I put a vertical line here, we only have one closed circle. The other one's open, so it doesn't touch at 2 points, so it passes the vertical line test. So that's why step functions are functions. Next page talks about some characteristics of a step function. So the domain of the function is the set of all real numbers. If you look back at our graph, every x value we can account for. We could have 0.99999 and we'll get a y value for it. So the domain is all real numbers. The range is the set of all integers, which integers we said are whole numbers. So our range would be like -2, -1, 0, 1, 2. Only whole numbers. You'd have to list them out in your range. Our parent function, the others just talk about the parent function. So the parent function has a y-intercept at 0, 0. X-intercepts in the interval of 0, 1. So this is just for parent function. These last three will change if you have transformations happening to it. In example 8, we have a piecewise function. So piecewise functions are similar to just normal functions. It's just talking about different pieces of it. So instead of having a graph that's just in the form of y equals mx plus b, where we can plot our whole line, this is a line, but it's only talking about the x values of that line that are less than or equal to 1. So we've got two separate lines here and just two pieces of those lines. So let's start by graphing our first one. So I'm going to graph the first line. So this is in the form of y equals mx plus b. So we know that it's a line. There's a couple different ways that you can graph it. You can graph the whole line and then just erase the part that you don't need. So we'd only keep where x is less than 1. Or you can plug in points. So if we plug in points, always start with the x value that's given. So I'm going to plug in 1. So I have 2 times 1 plus 3 would be 5. So my point here would be 1, 5. So I'm going to go to my graph. I go to the right one and up 5. Do we have an open or closed circle at this point? Closed circle. When you have less than or equal to or greater than or equal to, it is a closed circle. If we had greater than or less than, it would be an open circle. So that equal to makes it a closed circle. So we found where our line starts. Next, we want to plug in another point that's going to give us direction for this line. You could just do your slope and figure it out from there. I think it might just be easier. Let's plug in another number. It has to satisfy this interval though. So what's a number that we can plug into x that is less than 1? 0. So we have 2 times 0 plus 3, which would be 3. So my next point would be 0, 3. So we're going to stay at 0 and go up 3. You can keep plugging in as many points as you want, but you really only need 2 points to draw a straight line. So this would be our graph. So you always start at the number that you plugged in first. So start at where your interval is. X is less than or equal to -1. So that's our starting point. Then the line goes through the second point and it has an arrow. It's just a piece of this line, but it gets cut off where x is 1. Any questions on our first piece? All right, let's graph the second one now. So again, I'm going to start by plugging in the number that's given. So when I plug in 1, I have -1 plus 4, which would be 3. So my point here is going to be 1, 3. Do I have an open or closed circle here? An open circle. So I'm going to go to the right one and up 3 and put an open circle. Now we want to see what direction this line's going in. We have our starting point, but we need the rest of the line. What's a number that I can plug in for x? 2. Sure. Anything that is greater than 1. So let's plug in 2. So we have negative 2 plus 4, which would be 2. So I plugged in 2 and got 2. So I'm going to go the right 2, up 2. Once we have 2 points, we can draw our line. If you want to plug in more points to get an idea, better idea of what your line's doing, you can, but you don't need to. Bless you. So this is the graph of our piecewise function. Your graph of a piecewise function will always be a function. So it'll always pass the vertical line test. So if you had a line like, I'll draw it down here. Let's say we had one line that goes this way and then the other line that goes this way. You did something wrong because this would fail the vertical line test. So it's always going to be a function. So it will always pass the vertical line test. Any questions here? All right, last thing we're going to talk about is even and odd functions. So to test to see if a function's even or odd, we can plug in a negative into the x. If we get our original function, it's going to be even. If we plug a negative into x and get the opposite function, so a negative for everything, so everything in our function changes signs, it would be an odd function. Another way of doing this instead of plugging in negative x, so like other than doing it the algebraic way, so you can plug in a number and its opposite and test to see if it's even, odd, or neither, depending on your result. So I would say plug in, it could be any number, but I would say 2 and negative 2. It has to be any number other than 1. So the next easiest number to plug in would be 2 and negative 2. Obviously, if you had square roots, you might want to do something like 4 and negative 4, just to make it easier for you. But any number and its opposite, if you get the same answer, your functions are even, or your function is even. If you get opposite answers, then your function's odd. And then if you get totally different answers, then it would be neither. And then one other thing to add here. If it's an even function, it's symmetric to the y-axis. So it'd be something like, could be a parabola. Could be anything that's symmetrical about the y-axis. If it's an odd function, it's symmetric to the origin. So that would be kind of something like an x cubed graph, where it looks like this. So if you take your graph and flip it upside down, you'd have the same picture. That would be something that's symmetric to the origin. So in example 9, we're going to determine whether each function's even, odd, or neither. So you can either test it by plugging in negative x and figuring out if the signs change or if it stays the same. I think it's easier and less room for error if you plug in numbers. So I'm going to plug in 2 and negative 2. So when we plug in 2, we get 2 cubed minus 2. What's 2 cubed? 8 minus 2 would be 6. When we plug in negative 2, we have negative 2 cubed minus negative 2. What's negative 2 cubed? Negative 8 minus negative 2 would be plus 2, which would be negative 6. So if we get opposite answers, is our function even, odd, or neither? What? Odd. Since our answers were the same number but opposites, our function is odd. So A is odd. Any questions there? Let's do the same thing for B. So again, I'm going to plug in 2 and negative 2. So we have 2 squared plus 1. 2 squared is 4, plus 1 would be 5. When we plug in negative 2, we have negative 2 squared plus 1. Negative 2 squared is 4, plus 1 is 5. So is our function here even, odd, or neither? Even. We got the same answers, so our function's even.